this kind invitation. The topic of the talk will be quantum measurement cooling. It is a work that has just been published in PRL, also with a coverage in physics, so we are very proud of it. And it's basically a let's say a new way or a way that was not investigated before to fuel heat engines. The idea is to use the measurement process to fuel a machine. So probably the best way to illustrate this is by comparing with previous standard cooling concepts, or more generally concepts for powering engines. So here, panel A here basically shows the standard cooling by or driving cooling by time-dependent driving. Okay, here you have a cold body, a hot body, some engine, and you are driving the engine by means of time-dependent driving, and that can steer heat from a cold body to a hot body. This is what happens in our households with a home refrigerator. This is the refrigerator. You have the electrical power, and you take heat from the food and put it to the rest of the house. This is another standard concept which dates back to Maxwell. Namely, you make a measurement on the machine, and depending on the outcome, you apply different drivings accordingly in order to steer the heat from the cold to the hot body. I think of the Maxwell demon. That's what it does. There is this little intelligent being that looks at particles, and whenever he sees, for example, a hot particle, opens up a door and let it go or not let it go. So that's, let's say, cooling by feedback loop. So the new idea here is this, which in a sense combines elements from the previous ones. There is a measurement going on here, but now this is a quantum mechanical mechanical measurement. And as you know, the measurement process in quantum physics can be very invasive. That means it can be accompanied by energy exchanges. So why not using those energy exchanges as a fuel for the engine? So in quantum measurement cooling, basically, what was the time-dependent driving in this standard scenario is replaced by a quantum measurement process. And the interesting thing, and also probably one of the reasons why this work attracted attention, is that a specific property of this quantum measurement cooling mechanism is that you don't need to do feedback to make this thing operate. So that marks a distinct difference with Maxwell demon, where after the measurement you have to do feedback control. But in quantum physics, exactly because the measurement is invasive and exchanges energy already, if you engineer things properly, you can you can steer the heat without doing the feedback. Basically, without even recording what was the outcome of the measurement. So this is just for you to get a general overview of what is the idea. So before I describe this quantum measurement cooling in detail, let me also show you simple implementations of these two standard concepts, so that hopefully our implementation of the third one will become more clear. So let's have a look at standard cooling by time-dependent driving in a quantum mechanical setup. So in a setup where the working substance is a quantum system. This is the simplest thing, one of the simplest things one can come up with. Your working substance is, think of it as 2 qubits, these balls here, 2 qubits. So two-level systems. And think of a 2-stroke cycle. So in the first stroke, you apply some time-dependent driving to your 2 qubits, which you can model. Is there a laser somewhere? Here, yeah. Okay. Yes. So you can model the 2 qubits with their Hamiltonian, and then you can model this time-dependent driving as a time-dependent interaction between them, which is turned on and turned off. So the first stroke, you operate on them by some unitary, which you can implement by choosing an appropriate interaction Hamiltonian here. In the second stroke, you let each qubit separately relax to thermal equilibrium by interaction with a thermal bath. So this top qubit thermalizes with a hot bath and goes back to what was its initial state here, which was thermal. Sorry, I didn't mention that. So you start from each of them being thermalized with their own bath. You do something on them, and then you let them thermalize and go back to the initial state. And this way you do a 2-stroke engine. In the first stroke, there is a unitary evolution. In the second stroke, there are thermalizations with the baths. So the evolution of the density matrix that describes the 2 qubit is from standard quantum mechanics. You can easily calculate with standard quantum mechanics formalism the energy exchanges in both qubits as a consequence of this driving. So the interesting thing is that these energies that each qubit, the energy that each qubit acquires is in fact nothing but the heat that it will release to the bath, because it will go back to the initial state. So we can really assign the meaning of heats to these two quantities. Those are the energies that go into the baths. So let me show you one way in which this thing can work as a cooler. You start, as I said, with the 2 qubits each in their own thermal equilibrium, and then you do a swap operation. So swap operation is such that if one qubit is in the up state and the other is in the down state, it flips them. And if they're both up, nothing happens. If they're both down, nothing happens. If you do that, and if you choose the level spacings of the 2 qubits properly, namely, if you choose them in such a way that their level spacing is small, the ratio of their level spacings is smaller than the ratio of the 2 temperatures, the temperatures of the 2 baths, then as a consequence of the swap, the hot qubits becomes hotter, so it will reach a new temperature. But here is the inverse temperature is beta 1 prime, given by this expression. You see here, this has become smaller than it was before because of that inequality there, so it means this becomes hotter. And at the same time, the other qubit becomes cooler. So aftermath is that in the second stroke, the energy will go from here to here, and it will be, and most importantly, it will be withdrawn from the cold bath. And the initial condition will be restored. So you do swap thermalization, and in this way, little by little, you take heat from here, basically from a cold bath, and you transport it to a hot bath. This is one way to realize that standard thing. let's see in the same, let us see now in the same 2-qubit, 2-stroke scenario, how can one implement feedback control. Now imagine that the 2 qubits have same level spacings. And now imagine to do conditional unitaries. As I said before, in feedback control kind of operation, you make a measurement, and depending on the outcome, you do different things, hopefully in a smart manner. So let's see what is a smart manner to do cooling in this scenario. This is one way. You do, at the beginning, you do a measurement of the energy of each qubit. Okay. There are 4 possibilities. Either you find both of them up, first is up, second is down, 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 and down, up. In these first 3 cases, you do nothing afterwards. You do the measurement, and if you find your 2 qubits in any of these 3 states, you do nothing. But whenever you find the 2 qubits in this state here, so the hot qubit is down and the cold qubit is up, you swap them. And if the frequencies are the same, that doesn't cost you any energy, right? Because the energy of this state is exactly the same as the energy of that state, so that doesn't cost you anything. But what you have done by this conditional operation, you have basically altered the statistics of your state in such a way that this state here, hot qubit up, cold qubit down, is more probable because it occurs all the times that this came and all the times that this also came. So you enhanced the probability that this state occurs, and this is the state that in the second stroke will be such that energy will be withdrawn from the cold bath, because this qubit can only, it can do only one thing, jump up, meaning absorbing some energy from a cold bath, and this other thing can only do one thing, which is release energy to the hot bath. So in this way, one can make cooling by time-dependent, by feedback control without spending energy, actually. You have, basically, you're using information in a smart way. Now, the map that describes the evolution of the density matrix is more complicated. You don't have any longer a unitary map as before, which was this. Now you have a mixture of unitaries, and in fact a conditioned mixture of unitaries, which is written here. So you first have a projection here, this Pn, rho Pn, so projecting, which corresponds to the measurement that you do at the beginning. And then, depending on the outcomes, let's say if outcome n comes, there is a unitary un applied, and you have to sum over all 4 possibilities. So this is not a unitary map. Now let us come to our main idea. We do a measurement, just as I explained in the previous slide, but now instead of measuring the energy, so instead of measuring an observable which is diagonal in the eigenbasis of the density matrix, we measure in some other basis. Okay, so let me go back. Here, initially your 2 qubit, the state of your 2 qubits is described by a factorized product of 2 Gibbs state, and it is diagonal in the, each of them is diagonal in the Hamiltonian basis. And the measurement was done on the energy, so on the same basis. Basically, it was not an invasive measurement. No? You started with the diagonal state, you measure on the same basis where the state is diagonal, nothing really interesting happens. So what I'm saying is that if you, instead of measuring the energy, you measure something else that does not commute, that is not commute with the Hamiltonian of the 2 qubits, then you might inject energy or withdraw energy. So basically, there is an energy exchange associated to the measurement process whenever you look at an observable which is not commuting with the state of the object that you're looking at. And then, okay, then one basically has to find what measurement basis to choose in order for cooling to occur. So that was our first task. Here, I describe pictorially what one aims at. You want that, you want to make a measurement on, so let's again consider this 2-qubit 2-stroke scenario, and what one would like to do in that scenario is to make a measurement, joint measurement on the 2 qubits in such a way that this top one gains some energy and the other one loses it, so that in the next step, whatever has been gained here will be given to the hot bath, and whatever has been lost will be withdrawn from the cold bath, and overall you will have energy going from cold to hot. That's what we aim at. So now the maps that describes the evolution of the density matrix is a bit easier than the previous one. There is only a projection step here. Okay, and as a consequence of that projection, then you have a new state and possibly a new energy for qubit 1 and new energy for qubit 2. So in total, you might have energy changes in both of them, which, as before, can be identified with the heats, because those are the energies that are given or taken from the baths. The sum of them is basically the energy that you have, that the apparatus has lost. Some people call that quantum heat. For example, here, Elward and others would call that quantum heat. I don't know how to call it, but it's clear what I mean here, but this symbol delta E. That's the energy given or taken by the apparatus. And this delta E1, delta E2, those are the energy changes in each qubit or the heats that they exchange. So the whole thing here is now to figure out how to choose these projectors. PK, those are, as I said before, you want to measure on a basis psi k, so those are the projectors associated, the projector associated to those basis states. You want to choose the basis properly in order for that thing to occur. All right, so there is an important relation, mathematical relation, that I would like to show you, which is here. In the scenario that I've just described, if you sum the product of inverse temperature and heat of both of them, so if you do beta 1 Q1 plus beta 2 Q2, which is what I like to call Clausius sum. I call it Clausius sum because if you remember from the books in thermodynamics, this integral of delta Q over T, that was the main object of investigation by Clausius when he was studying thermal engines, and that's actually pretty much the same. This Clausius sum, in fact, can be expressed nicely in terms of information theoretic quantities. So the first one here is the Kullback-Leibler divergence or relative entropy between the initial state of qubit 1 and its later state. It's a non-negative quantity. Same for the second qubit. So you have this lag that's built up between the actual state and the developed state. And here there are total correlations between the two qubits, and there is also this term here, which is the total change in the von Neumann entropy. So these first three terms are non-negative, and also this fourth one is non-negative because our channel here, projective channel is a unital channel that corresponds to a non-negative delta H. So this sum here is non-negative. So an aftermath of that is the following. Combine this inequality with this equality and look at the signs of Q1, Q2, and delta E. You have 8 possibilities. So this inequality and this equality together, they rule out 4 possibilities, and there are only 4 that are left, which are this one, heat, which I call heat engine. Heat goes from hot to cold, and you deroute something for yourself. You gain some energy. Refrigerator is the opposite. You take energy from a cold bath and put it in a hot one. Heater, you put heat energy in and you heat up both baths. This is also possible. And another one, which I call accelerator, where energy goes from hot to cold, as it would naturally do, but at the same time, you're also helping that out by putting in some energy. Those are the only 4 possibilities that are allowed by this Clausius inequality, so to speak. So which one of these 4 things will occur depends on the basis measurement that we choose. So let me come to the results, because I think I did maybe too long of an introduction. So let's speed up and go to the results. But hopefully that helps understanding the results. So as I just said, there are 4 possibilities. So our first result was that depending on the ratio of the level spacings of the 2 qubits, some of those 4 are excluded. For example, if you are in this regime here, where the ratio is smaller than the ratio of the temperatures, you can only do refrigeration and heating up everything. Here, you can only do energy extraction, so the heat engine operation, accelerator, and heat up everything. And likewise here, there is only acceleration and heating up everything. As you can see, heating up everything is the simplest. I mean, it's something that you can always do, which is which is pretty nice to see, at least from the formalism here. That's what one would expect. Second result, now try to maximize the efficiency, for example, the refrigeration efficiency or the heat engine efficiency, depending on which range you are. As you try to maximize that, you find that the best choice of your basis is this singlet triplet basis, where basically you have to do this bell states between the up-down and down-up states. Those are the bases that, depending in which range you are, maximize the energy, so the efficiency, but also the energy extractions and energy output. And actually, the efficiency that you get is the same as the quantum auto engine efficiency, but the outputs are half of them. If some of you is familiar with the quantum auto engine results, there is here there is this extra factor too. Basically, your ability to do stuff is less when you have only projective measurements as compared to the situation where you have unitaries. Second result is that those maximal efficiencies, in fact, can be achieved even if you use higher rank projectors. So you don't have to project onto pure state. You can also project onto larger subspaces. For example, if you combine the first and the projector that projects on this space spanned by the first 2, and another projector which projects on the space spanned by the 3rd and 4th, nothing will really change, and you can still achieve maximal efficiency. So what is important here to stress is that you don't have to project onto pure state to make this thing work. And let me not comment further, because I want to state another result, that this special form of the optimal basis containing only states of the type AA and AB plus minus CD, as we have just seen, that's more general than the 2-qubit scenario. That is always the case for a 2-qubit working substance. So this is something that we saw from numerics first, and we were pretty much surprised. We didn't really understand why is it so. Took us quite some time to prove it formally, but we did. Let me just very briefly tell you what one has to do in order to achieve the proof. You have to express the energy changes in terms of the transition matrix. So here, for example, here, this is the final energy, this is the initial. You want the difference. The final energy is expressed in terms of initial population, final eigenvalues, and you have this transition matrix. Now, if you do this projective channel, this transition matrix is a product of some matrix Q times its transpose here, QT, and where this Q is a doubly stochastic matrix that has a special form, M-U-N, where U is some unitary. So in order to prove the result, what we did is to use Berkoff Theorem that tells you that any doubly stochastic matrix like Q is a convex combination of permutations, so that we could find the minimum of this expression here, the final energy, over all bistochastic matrices. But not all bistochastic matrices are of this form. Those that are of this form are called unistochastic. We learned quite a lot, and it's a subset of the set of bistochastic matrices, and it's in fact a topic of importance in the foundations of quantum mechanics. Rovelli talks about this, for example, in the context of interpretations of quantum mechanics. This opened up a Pandora box for us. But anyway, if you restrict the maximization to the subset of bistochastic matrices that are unistochastic using some result in linear algebra from the 90s, you will find that result. It was pretty challenging, and we had to work hard to get that. Another result is that generally for 2 qubits, in order to realize anything other than heating up everything, some of the measurement projectors must be entangled. So the measurement must be such that the post-measurement state is entangled. But anyway, also we saw that extremal efficiency occurs when the full density matrix is still diagonal in the initial basis. This is a bit an oxymoron, but this is what it is. Another result is that if you pick up the basis randomly, then you're gonna heat up everything on average. So if you average also on some on the invariant measure for the unitaries, you're gonna heat up everything. This is also pretty intuitive, but also not so easy to prove. And last result that I'm going to show you are outcome of Monte Carlo samplings. So what we did is we just pick up unitaries randomly from the SU4 invariant Haar measure, which means we picked up basis randomly and see what happens on average. So and see the statistics of the, so to speak, the SU4 hypersphere. Basically, in each point of the hypersphere, one of those 4 possibilities will be realized. So we wanted to basically quantify the measure of the regions where heat engine operation occurs, refrigeration occurs, to see how big they are. How probable is that you get one of those? For example, let's look at this picture here. This is for the probability of heating. It's plotted as a function of the ratio of the 2 qubit level spacings. Let's look, for example, at the red curve, which is for a specific value of temperature ratio. You see the probability is always larger than 1/2. In fact, it goes up. It's pretty much the whole, apart from this region here, very close to 0, pretty much the whole hypersphere would result in heating up everything. You see, probability is very close to 1 in this region here. Accordingly, if you look, for example, at the, let's look again at the red one, probability of doing heat engine operation looks big here, but only because we had to multiply everything by 10 to the 4. So the measure in the R space of those bases that would realize heat engine operation is 10 to the minus 4 or 5 of the whole volume. So it's very improbable that you pick up a basis randomly and you realize heat engine operation. And also, if you are able to realize that optimal bases that make the heat engine operation, a little bit of noise will kick you out of that region, and so it's not practically feasible. But let's look at cooling. Of course, it must be it is non-zero below a certain point, which is the ratio of the two temperatures, as I showed you before. But see, it goes to 1/2 as you get closer and closer to 0 with this ratio, which means that if you choose the parameter, this ratio small enough, the region where refrigeration occurs can become larger and larger. So it basically, if you are able to realize the maximal basis and you have some noise on the basis, on experimental noise on the realization, it's not gonna do a big harm because you will still remain within the region where refrigeration occurs. So the whole point of these pictures was to show that cooling is experimentally feasible. It's robust to noise, very robust. Can be very robust to noise if you choose the parameters appropriately. All right, so I think I'm done, right? So just the last, I just flash it without going into the details. We also investigated how this could be implemented experimentally using superconducting devices. So by combining basically circuit QED with other kind of devices that are realized in the group of Peccola, for example, or also Giazzotto, integrating, methods from different groups, one could actually make this thing realize it practically. So, but I don't have time to enter into that. And with this, I thank you for your kind attention. It can continue to work also for weak measurements. Yes, yes. Yes. Okay, maybe I can elaborate a little. Of course, one has to, again, choose the right measurement operators, let's call them, to make this work. We didn't